everyone. Welcome. Yeah, we have many participants here, and I'm Haixia Lü, currently working at Wuhan University, and now leading the executive team of the AOGS Low Latitude Atmospheric Research Group. Now I will introduce our speaker today, Dr. Deepak Kumar Karan. He's a distinguished research associate at the Laboratory for Atmospheric and Space Physics, affiliated with the University of Colorado, USA. He completed his PhD degree at the Physical Research Laboratory in India. He's a dedicated scientist with extensive expertise in ionospheric thermospheric studies and the impact of space weather on Earth's upper atmosphere. His research contributions include 8 first-ordered, 3 second-ordered, and 8 co-authored peer-reviewed papers, accumulating more than 310 citations. Dr. Karan has made significant contributions to the scientific community. He served as the primary convener in 7 sessions at various international conferences and meetings, including AGU, AOGS, and CEDA. Additionally, he has reviewed over 20 manuscripts for 10 peer-reviewed journals and participated as a judge in presentations at 10 international conferences. His research work has garnered recognition at the national and international levels. His PhD thesis received the Best Thesis Award in Physical Science from GSA India. And in 2019, he was honored with the Yaga Young Scientist Award. Dr. Deepak Kumar Karan's dedication to advancing understanding of atmospheric and space physics, coupled with his numerous accolades and active involvement in professional services, positions him as an invaluable asset to the scientific community. Currently, he is actively engaged in NASA's Gold mission. In today's presentation, he will share some of the latest and intriguing findings on the Equatorial Ionization Anomaly and the Equatorial Plasma Bubble based on gold observations. So, Dr. Deepak Kumar Karan, now you have the floor.
Hello, everyone. Thanks, Professor Haixia, for this kind introduction. First of all, I want to thank the AOGS-RAC LLWG committee, which is Low Latitude Ionospheric Research Working Group, for providing me this opportunity to share this work that I'm currently doing with the Gold mission. And particularly, I thank Professor Haixia for inviting me for this. As you already know, okay, so before starting, can I take questions in between, or we'll take questions at the end?
Question better in the end. Yeah.
Okay, that sounds good. So as you can see, the title says the Illuminating the Enigmatic Equatorial Ionization Anomaly and Equatorial Plasma Bubble, Insights from NASA's Gold Imager. So in this talk, what I am going to do is, I'm not really going detail in the science part. Rather, it will be more informative for the community because the NASA's Gold Imager has found out really interesting and some new observations from the space. So I really want to introduce those observations to the community through this presentation. If someone really wants to go in detail, we can take those questions at the end. Just to start with, the first question comes, if you have looked at the title, okay, what are those EIA and EPBs, which stands for the Equatorial Ionization Anomaly and Equatorial Plasma Bubble? Briefly, what I want to say is that the atmosphere that we experience here, sitting at the lower atmosphere in our house here, it is neutral. We can breathe in the air and we can breathe. So we are fine. But what if we will go to altitudes of 100 kilometer, 200 kilometer, 300 kilometer, what will happen? The atmosphere is getting thinner, first of all. And the second most important thing is that you will find electrons and ions in that atmosphere. That means that atmosphere is ionized. So it doesn't mean that there is no neutrals. Yes, of course, the neutrals are there. So if we are studying the neutral aspect of that atmosphere, then it is called a thermosphere. But if we talk about the ionized particle, how they behave, what is happening, what are the dynamics happening with the ions and electrons, that part is called ionosphere. So it is a coupled system, ionosphere and thermosphere in the upper atmosphere. So these ions, the ions and electrons which present in the upper atmosphere, they are affected by the Earth's magnetic field, which is really, really the crucial point for the upper atmospheric investigation. In this left plot, if you look at these solid black lines, so these solid lines, this is the Earth's these are the Earth's magnetic field lines here. You can see this is the Earth's magnetic field line one here, another, this is the magnetic field lines here. So, and this is the equator, and this is geomagnetic equator. If you look at the orientation of this magnetic field line above the geomagnetic equator, you will see this is kind of like a horizontal. So that is very crucial. That geometry, horizontal geometry, is very crucial for creating electrodynamic processes over the equator. One of those processes is that in the around 100 kilometer, which is the E region, we say E region, the electric field is eastward. And because of this magnetic field, there is a upward drift of the plasma that happens. And because of the upward drift, it takes the plasma up. When I'm saying plasma, both the electrons and ions, they gradually move up. And what happens after that is really interesting. And this right side picture, it is a movie. So on the right hand side, you can see this is the geomagnetic equator here. And now you see this red band, red color thing, that is the air glow emission. That is the upper atmosphere. The altitude where you are seeing the red line, it is around 200 to 250 kilometer altitude. And that at that altitude, due to some processes, 630 nanometer emission comes. So that which falls in the red line. That's why we are seeing it is a red line. And again, it is an image, so they wanted to show the ionosphere in that direction. But the important point is that the plasma from the equator, they are moving up, and gradually they are following the magnetic field lines and going to either side of the geomagnetic equator. And if you will see, they are going up and following the magnetic field line, going to either side of the geomagnetic equator, to this side and again to this side. So as a result, we see more electrons at this area and also at this area. The geomagnetic equator of the Earth falls over at this here at this location. So we see bright, like enhanced electron density on either side of the geomagnetic equator. So this is called, this process, like something is going up and it is spreading to either side of the geomagnetic equator. It feels like a fountain, like as if the water is going up and falling on either side. So that's why it is called the fountain effect. This process is named as the fountain effect, but it was discovered around 1940s. And this is known as the Equatorial Ionization Anomaly. So when I'm saying the EIA, basically it says the two bright electron bands on either side of the geomagnetic equator, and they generally those are really 12 to 15 degrees away from the geomagnetic equator. So that is a basic understanding of the EIA. I will use the term EIA throughout my talk right now. Sometimes I may use Equatorial Ionization Anomaly. On what factors does it depend? As I told that it pumps the plasma up. So that means it depends upon the electric field, which created that vertical drift. So the electric field is created by some wind mechanism. So eventually it depends upon the wind and how much electron is present in the ionosphere. Also, that is a factor. And also the conductivity. These are the factors on which the EIA depends. This is a basic idea. Now, the second question is, well, what was that equatorial plasma bubbles that was in the title, which in short, we say EPB. To understand this, think of the electron density. When we think of from 100 kilometer to 300 kilometer in that altitude, if we look at the electron density profile, you will see a very smooth pattern. But sometimes what happens, particularly after the sunset, when the sunset happens at the lower thermosphere, the recombination happens faster. Because of that, the electron density falls rapidly. So what is happening? So this is the thermosphere. Think of like a slab, and at the lower part, now the electron density is less, but in the upper part, electron density is more. So this resemblance, like a heavier liquid is sitting over a lighter liquid. And here I'm giving a example, but in reality, it is the plasma density that matters in the ionosphere. So now this is kind of unstable. Any kind of perturbation in this left side diagram, a cartoon which is shown, this lower panel, this is now the lighter density region, and the upper part is the denser. So this is unstable. Any kind of perturbation in the lower part of this unstable system triggers instability, which gradually goes up goes up to higher altitude. Think of like when we are inside a pond or inside a swimming pool, go inside the water, and when we start making bubbles from our mouth, the airs, they gradually move up. A similar kind of situation is happening here, and at that moment, what happens? The path where this bubble gradually moves up, it disturbs the medium. That means some irregular things are happening there. So the regular electron density profile is getting disturbed, and we say it is as irregularity is happening over that path of the bubble. So on this middle panel, you see, okay, here, this is a radar observation. The y-axis is the height here, and the x-axis is the zonal distance east to west. Don't worry much about that. So what you need to see is that these black color things are some plasma. Think of some electron, kind of like electron density region here. And these are perturbed here. And one satellite is just passing from left towards right. And it measures how much is electron, what is the electron density along its path, which is plotted here. Now, look, you see what you are seeing. A lot of fluctuations are happening, going up, down, up, down. That means the electron density profile, the electron density distribution is really disturbed. So this is how people have observed the plasma bubbles. The irregularities, the plasma irregularities. And there are different kind of observation techniques that we use to observe the ionosphere. And depending upon the observation technique, we see the signature of the irregularity in different way. Accordingly, different kind of nomenclature are being used in the community. If it is in digisonde, kind of like a ionogram, we say it is as a spread F. And in radar, GPS scintillations are used. In satellite, bite out, depletion, bubbles. In optical imaging, the word is used as bubble, which I am going to show in my next slides. And in simulation modeling investigations, people used the magnetic flux tubes, bubbles, these kind of terminologies are used. I'm not going in detail for the production mechanism. There is a when I looked into all the talks in this LLWG seminar series, there is a talk by Professor Tatsuhiro Yokohama, who talks really fantastically about how these plasma bubbles are forming, how they are being evolved. So I really request, if you want to know more about the bubbles, this is the talk you want to listen to. Well, now the question, what is the importance of these investigations? I am talking about the EIA, PVs. Now, why do we care about it? Like a common man thing, like, okay, my friends can ask me, why are you studying these things? Why would I care about it? Well, my answer will be like this. We all depend upon the GPS technology. What is the use of GPS? We really need not to explain. Everybody knows. In air traffic control, I am just pointing out few of the things here. That means what it says, that in our day-to-day life, even at the moment when I'm talking, people are using. We are using all these or the GPS technology and satellite communication, and this depends upon the radio wave signal. So the radio wave signal is coming from the space, and it passes through the ionosphere. And during that plasma irregularity path, if the radio wave signal is passing through that path, the phase and amplitude of that radio signal changes. And what it causes scintillation. When the amplitude and phase of that radio wave signal changes, we call it as a scintillation. So it generally disturbs the communication and navigation signal. It can use the signal, whichever is coming from the space, it can be delayed. It can go anywhere else. I mean, and also it can interfere. There will be interference, distortion, these kind of things will happen. And I mean, I really don't want to explain what kind of hazard and what kind of uh, important role this can really create. So we need to understand at what time these irregularities are happening, how they are evolving, what is the condition which triggers them, can we really forecast them? These are some investigations which really needs to be carried out, and we need to be really upfront in that direction, so that we can save our life. It is really important for socio-economical contribution. So that's why this is the important aspect why where these investigations can contribute for a common man or for a general life also. Well, now I believe that I have given you some idea what is EIA and what is EPV. Now, how does this look from space? Why I'm bothering about space? Because my talk I am going to space observations. That's why. So this is now this is the Earth. You can see. Think yourself as a satellite which is far away from the Earth. Think yourself as the camera. Now you are looking at the Earth. So you are taking, at some point of time, you are seeing this kind of thing. So these bright line here, these and this is called the EIA. So this is the north crest of the EIA. This is the south crest of the EIA. And this green line is the geomagnetic equator. And what is equatorial plasma bubble? How does they look like? They look like this depleted band structure, like one here, one here, one here. There are many here in this particular frame. So these structures are the plasma bubbles, and EIA crest are these north and south crests. Well, this is the basic understanding. Now, with this, let me go about the gold mission, and I'll quickly jump into the observations. Just briefly, what is gold mission? About gold mission? It's a NASA mission of opportunity which images the IT system, ionospheric thermospheric system, from geostationary orbit, which is like 36,000 kilometers away from the Earth. And the subsatellite point of the gold is this point, which is minus 47.5 degree longitude, and the field of view is shown by this area. And gold sits at that far away from its geostationary orbit. All the time it looks at this area. So it moves along the Earth. So whenever this area is in day side, gold takes daytime observation. When this longitude is in night side, gold takes nighttime observations. Well, in this present talk, I will be focusing on the nighttime observations. So how does the gold take nighttime observations? That is really important to appreciate the results that I'm going to show. So this is the sunset terminator. As you can see, on the left side it is day side, on the right side this is the night side. So gold starts the observations from 1 hour after the sunset. So from this longitude, gradually goes towards the eastern longitude, and it takes around 12 minutes to scan this area. And after that, it comes back to the southern hemisphere, does the same thing. And meanwhile, you understand that the sunset terminator gradually moves towards the west. So the start longitude will gradually move towards west. And in this movie here, you will see the each image, the how gold is taking. The red line is the sunset terminator. Now this is one image, second image. Observe that, notice that the sunset terminator is gradually moving towards the west, and the starting longitude is also moving towards the west. So from west of African longitude sector, now it is scanning the Atlantic. Now it is entering towards the South American longitude sector. Yeah. So in each evening, it takes around 24 to 36 images, and each longitude is observed 2 to 3 times, like almost 2 hours. So multiple times scanning is there. So if we want to see any structure, its evolution, this is really good. And this is another image, a similar observation, just in a different color scale, another day. For out of curiosity, just I wanted to show. But you can see the EIA crest, north crest, south crest, and the plasma bubbles here. The structures are here. These are the plasma bubbles. The important point of the plasma bubble, one thing I just want to point out here is that these are mostly according to their geometry formation mechanism, evolution formation mechanism, they need to be straight perpendicular to the magnetic field line. As you can see here, this is the geomagnetic equator, and the plasma bubble is straight line. This is perfect. Okay, this is an important piece of information which I will be using after 5 slides. Well, so with that, I will bring 3-4 of important findings. The first one is here. We, in 2020, we looked at all the gold images in the month of September, December, and March. Each evening, we looked at the images, calculated the North EIA crest location and the South EIA crest location, and which is shown here. The red line is the South EIA crest, North EIA crest, and the blue cross is the South EIA crest. What you are seeing is the first thing. Well, in September, December, March, these are completely different. Very good. The second thing, in a single month, if we go from west to east in the longitude, also it changes. So the two things is strikingly coming out that there is a longitudinal variation in a single season, and that longitudinal variation has a seasonal dependence. It changes from season to season. And the third point is that the North EIA crest and the South EIA crest also don't go in a similar fashion. It goes similar fashion in September, but not in December. In March, not really over this longitude. So this kind of information, what we have got is really interesting. And in this paper, we have investigated the reason why these are happening. And we found out that, okay, before going to the punchline here, let me show you what is happening in 2020. We extended that analysis in 2020. This is not published yet. This part is under preparation. We saw that a similar kind of variation in the in season to season, but if you look at the values here, it is around like 12, 14, but if you go here, it is around 10 or 12. The difference is that with the increasing of solar activity from 2020 to 2022, the EIA crests are going farther away from the geomagnetic equator. That is the finding here. But the seasonal variation, the longitudinal variation with season is somehow similar. So this is a very crucial piece of information which we have found gold has produced from the nighttime observation. And here I want to point out that because of the longitudinal scan, same longitude each evening we are scanning, that gave us the opportunity to do this kind of analysis, which was not possible before. And now we didn't know what is happening over the Atlantic Ocean. But with this, from the space, really we know that, okay, what is happening there. So this is really crucial. Now, the second piece of information, I'll go to the space weather impact. We all know that the space weather has a very, very strong impact on the ionospheric thermospheric system. So just to give a simple idea about what is space weather, when I'm talking about any kind of disturbance, huge amount of energy is coming from the sun, bombarding to the earth, and through the magnetic field line, going to the pole, doing some electrodynamical processes, the wind is setting up. Even sometimes the electric field can really penetrate to the equatorial ionosphere, and because of those electric field and the wind, compositional variations, these brought changes in the ionospheric thermospheric system of the Earth, and these are because of the space weather. And we really worried about that because space weather can do tremendous hazard and tremendous changes in the ionosphere. So we thought, okay, let us investigate one CIR kind of storm. This 2020 September 27 was a CIR storm, as you can see, looking at the changes in the solar wind parameters. These are really fluctuating. Well, in the ABC panel, I am showing the solar wind parameters. So interplanetary electric field, magnetic fields, proton density, proton speed, temperature, pressure. And bottom panel, it is the geomagnetic indices. You can see it is a CIR kind of storm. My focus is on the day 271 here. This is 271 here. 271 starts here, it ends here. Look at this time. At this time, we see the IMF is getting negative, strong, like really changing here. The interplanetary electric field is getting positive, and we see speed is increasing. The wind, the solar wind speed is increasing around like 600 meter per second. It is increasing by 200 meter per second. And the density is also increasing suddenly, temperature, pressure. So this is a very interesting time. Why I'm really emphasizing it, that just this coincides with the sunset time with where the gold was taking observations. And just after that, gold started its nighttime observation. And these are the images, composite images of from the gold on that evening. And this in the panel E, I'm showing the red is the North EIA crest, and the blue are the South EIA crest, which are obtained from these images. And this is the brightness, North EIA crest brightness, South EIA crest brightness. On the right panel, I am showing this is the quiet time averaged value, because I wanted to really compare how much shift in the crest has happened on that evening itself. So I need to compare with respect to the quiet time in the previous days. So on the right side panel, it is a quiet time plot. So let us not worry about it, but this is important. On the left-hand side, this shows the shift of the North EIA crest on these 6 disturbed days. The important thing is 271, which was that I mean this day 271. We see that maximum shift on the North EIA crest has happened, and also the South EIA crest has happened. It is really significantly coming out. Well, what is happening on that evening itself? And remember, it is happening over a wide longitude range. It is not just a small longitude. It is over, like if you go for, this is geomagnetic and geographic. I always show the geomagnetic longitude and geographic. So it is over 30 degree or 40 degree longitude. So for that, I was really lucky that the photo laser decision day was operational for that whole month. And this is the HMF2 variation in the evening time on that whole month of data. Very significantly that, okay, something is really significant here, the day 271 going really up. This is showing that the height of the ionospheric layer has gone up on that day itself. And we looked at the model prompt penetration in electric field, which shows a positive excursion at that time. So this shows that the prompt penetration electric field has enhanced the net electric field, for which the ionospheric layer has gone up, and it has pumped the plasma to further away. It has pumped the plasma further away, for which the EIA crests has moved further away. So this is really interesting. in this plot, I was really curious, okay, what is happening to the plasma bubble? Are they increasing? Are they decreasing? We know that in the community, it is a debate all the time that whether the geomagnetic storm enhances or it it decreases, or what is happening to the geoplasma bubbles. So in this plot, I am showing the x-axis is the longitude, y-axis is the day of the year for that whole month. On the evening of 271, I saw that each cross shows the location of a plasma bubble that is detected in gold image. So whenever you are seeing one cross, that is basically plasma bubble at that longitude on that day. So in this shaded region where we saw maximum separation of the EIA, I see that more plasma bubbles are appearing on that evening. So this is observation. I believe that what we saw, the prompt penetration electric field, enhancing the net electric field, moving the plasma, the ionospheric layer up, that is making the ionosphere more conducive for the irregularity formation, for which we see more plasma bubbles. Well, then I thought, I was always thinking, what is happening during a CME storm? I was waiting for that. This is the summary, I have already told about it. I was waiting for a CME kind of storm until I found one recently, April 23, 2023 geomagnetic storm, which is a CME G2 kind of G2 level, very strong geomagnetic storm. I thought, okay, let me do similar kind of investigation on this for this case and what I am seeing here. And believe me, I saw something spectacular in this on this day. A similar kind of plot here, the geomagnetic indices on the ABC panel, the solar wind parameters on the panel ABC, and the panel D, it is the rate of change of CMH index. And this red is the is the time when gold is taking observations. So when gold is taking observation, if you will see, it goes through a main phase, particularly this phase here. But some people will investigate this as the main phase, but since I am looking at the gold, so I will say that consider that I will show gold observations during this time. And what is happening during that time, you see rapid fluctuation in the IMF-VG component. So, well, that really can do something to the plasma, to the images. Let's see. Here I am showing some of the images in that particular evening. On the upper panel, ABCD, you see the EIA crests are brighter. The first thing, EIA crests are brighter over there. And in the bottom panel, where I am going to the Atlantic and South America longitude sector, the EIA crest brightness is really going down. The second thing is, look at these structures. These structures here, these are completely absent over the South American and Atlantic longitude sector. That is the, a very interesting observation here. We see plasma irregularities to the east of 30 degree or 25 degree longitude, and where we see brighter EIA. I found out how much shift in the EIA crest has happened. As you can see over that longitude, over this west of African longitude sector, I see that the EIA crests are really getting further away comparatively to other longitudes. So this is the shift in the EIA crest locations. It is the difference here in this storm, the CME case, is that it is happening in a narrower longitude range, around like 10 degree. But in the CIR, it was over wider longitude range. Now, what is happening to the plasma bubble? Here I am showing those images in geomagnetic coordinate system, just to show that plasma bubble should be aligned along the magnetic field line. That means the plasma bubble should be straight here, but these are really curved. This is really, really interesting. And I thought, okay, let me calculate their tilt angle. How much tilt? What is the tilt angle? And I found that the tilt angle is coming to be 42 degree, 52 degree at latitudes around 35 degree geographic latitude and 25 degree geographic latitude. Then I thought, oh, wow, is it really how much Is it really significant comparatively to the literature? But I searched for the literature, found out to really find what is the reported westward tilt. Unfortunately, people have not reported that angle that frequently. So I recalculated some of the paper and values, the westward tilt of the plasma bubble in those cases, and I found that the number is coming out to be 28, 26, 25 degree kind of thing. So, but in this case, when it is coming 42, 52, it is really significant. It is the westward tilt. And I forgot to mention this, the plasma bubbles have really reached mid latitudes or like 36-degree magnetic latitude. With a foot point of 36-degree magnetic latitude, it corresponds to 4,000 kilometer apex altitude. When I am seeing the plasma bubble morphology, the C-shape, reverse C-shape kind of structure, I always try to find out their drift, what is their drift velocity. So this is kind of a chaogram I was curious to just to investigate. So I took 3 latitude range. One is the south EIA crest latitude, which is -30 to -20 geomagnetic latitude. At the middle panel, it is the equatorial, -7 to 7 degree geomagnetic latitude. And in the panel C, it is the north, 20 to 30 degree. So I am looking at 3 different latitude range, and I'm looking at the location of the plasma bubble from one image to another image to another image, and I want to see how they are moving. This is kind of a chaogram. Let us not go in detail. The summary is, what I found is that over the equator, the plasma bubbles are moving eastward at a speed of 120 meters per second. And at the north and at the south, those are moving westward at a speed of around 80 meters per second, which is interesting because I have never seen a westward drifting plasma bubbles like this. I have seen even though plasma bubbles are reverse shape structure, they also move eastward. But in this case, it is really moving westward and with a very, very large number. Like the velocity is significant here. So I thought that because of this reversal in the drift from eastward at the equator to westward at the mid latitude, that is contributing to the more change in the westward tilt. So I thought, let me do it at each 5 degree to see how it is happening. So as we go from A to E, you are going from 10 to 15, 15 to 20. Basically, you are going in 5 degree increment to the northern latitude. And look at the slope. Here it is like eastward, and slowly it is reversing towards the westward. And the same thing is happening in the southern hemisphere. Over the equatorial, it is more like flat. And as you are going further to the south latitude, it is moving southward. Moving westward, sorry. So this is showing again that westward tilt. And I calculated these values, what is the drift, what is the number, and then I plotted that drift speed with respect to the apex altitude to which it can map. So what we are seeing here is that as we are going from 350 kilometer to higher apex altitude, gradually near the equatorial latitude, it is eastward, and there is a transition happening around 1200 kilometer apex altitude, which corresponds to 18 degree magnetic latitude, and where the reversal is happening. And at higher apex altitude means higher latitude, it is moving westward, which we are seeing here. This figure is showing that the zonal drift speed is not linear all the way from 350 kilometer to 4,000 kilometer. There is a break to it. It is linear till around 1,500 kilometer, and after that the slope changes. So this kind of things was not reported anywhere before, and we didn't know how the change in the drift speed happens. Then we calculated and formulated some relationship between the zonal drift speed with respect to the apex altitude. Well, these are the findings from this case. So we see that CIR and CME are showing different kind of behavior, and particularly in this CME, in this case, we see mid-latitude plasma bubbles showing significant westward tilt, reversal in their drift velocities. So this is the investigation that gold is producing regarding the space weather impact, which is really interesting, and important piece of information for our community, because I think that the potential of this kind of study is we can do more investigation like this. It will help us for a forecasting of how much to what latitude it can really go, the plasma bubbles can really reach. So it will help in the forecasting of the plasma bubbles in a way. But at the moment, I really don't know the path how to go with that, but I see the potential here. Okay. I am towards the last part of my talk here, which is really, really interesting that gold has produced, and I am really excited about this result. What I am showing in this slide is different kind of plasma bubble shape. We know that the plasma bubble, it should be aligned along the magnetic field line to make it a straight. But because of the wind, altitudinal variation with latitudinal variation, and at the EIA crest latitudes, because of the higher drag, even the wind speed decreases. These kind of things contribute to the different shape of the plasma bubble. So we see sometimes reverse shape of plasma bubble structure in the this is in the Gubi measurement, the timed measurement, not Gubi. This is timed satellite measurement. In the all sky measure, we have seen reverse shape plasma bubble structure. Huba et al. In the simulation, he has shown straight reverse shape plasma bubble, C-shape plasma bubble. In gold, in one of my earlier paper, I have seen straight plasma bubbles. And recently in this geomagnetic storm cases, I saw these are kind of westward tilted plasma bubbles. What is missing here? C-shape plasma bubble in observation. And believe me, I am not finding C-shape plasma bubble in the observations, and which really and also the explanation to that. There is in modeling, yes, I see paper, there are modeling investigations people have done, but in observations it is limited. That is one thing, but that is not the focus of my thing. My thing is here. In gold, when it started observation in 2020 October, I am looking the data all the time, and these are the only two cases we saw these kind of structures. The C-shape, reverse C-shape are happening very close to each other, and in another case, they are just happening very close to each other, but in the opposite orientation. And the longitudinal difference is 6 degrees, around 6 degrees. So this is a very rare observations. And because why I'm saying this is interesting, I have seen C-shape, consecutive C-shapes, consecutive reverse C-shape in the gold images, but never ever these kind of things. So I proceeded to calculate the drift velocities. So the drift velocities, as you can see, the B1 is a C-shape structure. So it moves faster at the crest latitudes, and that the equator it is moving slower. Well, that explains the C-shape structure. Let us go to B3, which is a reverse C-shape structure. That means over the equator it should go faster. Yes, it is going. I mean the drift velocity that I have calculated is reflecting that. In between the B2 is a straight plasma. Look at the value at those three different latitudes at the north, equator, and south. It is like same. So it explains their shape. Now the question comes, okay, the drift velocities explains their orientation, but why it has happened? Why it is so rare? I don't have an answer for that. If we can think of it is a neutral wind effect, if it is electric field or a combination of those, or any conductivity is happening, well, will you believe if I will say that the neutral wind is changing it's within 6 degree longitude significantly, or the electric field is changing? It is hard to believe. When I said this to people without showing this picture, they're like, no, that can't happen. But when I show this picture, oh, well, there is a possibility. So it is up to us. It is to the community. What do we believe and what we know about the longitudinal variation, how much small scale longitudinal variability we really have understood. In one of my earlier, during the PhD time, during using the day glow observation, I have inferred that the daytime equatorial electric field can show a longitudinal variation within 3 to 5 degree longitude. That is in the daytime using the day glow emission. Well, the ionosphere, so that could be a possibility in the post sunset or just during the sunset time. But I believe this needs to be taken by the modelers, and we need to understand, because it is giving a challenge for our understanding, because we know that the plasma bubbles, the irregularities needs to be understood very thoroughly. And why I'm emphasizing here is that without the gold observations, these kind of things would not have been possible, because you need to observe each day the same thing, because these are rare things happening. So if you are doing 1 month observation, and we can say, oh, it is not happening because we don't see that. So this is really interesting. It just got published this week. This is my last slide of the talk. So as I told in my title, that I will show some enigmatic pictures from the gold without going in more. There are many interesting observations that we are finding, which one is on the left, and at the center it is during the night just after the Tonga volcanic eruption, where we see that the EIA structures are distorted, and at this longitude I can definitely, we can see there is a plasma bubble. The EIA crests are going further. At this location they are collapsing, and at these longitudes they are like kind of breaking, even going further away. So it is showing a interesting behavior. There is a paper by Ercha about this structure, but I thought to bring this up. This is a very cool picture. And what we have seen, that the merging of the EIA crest to form a X kind of structure. So this is another interesting piece of information for the plasma behavior. What is we are seeing from the gold. And yeah, so I thought just to show some of these pictures at the end slide. And here I will thank all of you for your time and for your attention. I will be happy to take any questions. Thank you.
Yeah, thank you. Thank Deepak for so many fruitful, results and sharing with us. And any questions from our audience participants? So interesting. I see different shapes of this EPB, right? The plasma bubbles. This X shape and the this C shape reversals occurs in simultaneously. So yeah, from your talk, I understand that we still don't know the reason, and the model cannot reproduce this phenomena, right?
You are correct. Yeah, I talked with some modelers to.
Yeah, that's so interesting. We expect that simulation can reproduce these features.
Yeah.
Right.
And SAMI 3 was run for this case, taking the Wakamax input, and for these two cases, but it couldn't produce these kind of things. So definitely the small scale variability is missing. Even Wakamax is not able to catch that. Again, it is a model. So I think some kind of, I mean, my understanding is that some kind of what is this called, vortex kind of thing is happening over that location. Again, I ask myself why it happened during that time, because this is geomagnetically quiet time. What would have caused that? But but just thinking of the wind changes with height and with latitude, it gives me an impression that some kind of vortex is happening there. Some kind, but I don't know the reason why it would have happened. But that can explain.
Hi, Deepak, it's Trinesh here.
Yeah, hi Trinesh. Yeah.
So it's nice talk. So my question is, have you find any correlation of the electron plasma temperature? Do we get similar kind of irregularity which this picture shows?
The electron, yeah, I mean, there is, for these cases, I looked, there was a satellite icon which was taking some measurements, but the thing is, it is close to the South Atlantic anomaly here. and at that longitude the sensitivity goes down and data are not reliable. So I didn't have any success looking at the those kind of data sets to see really what is happening to those.
Like, I want to understand, is the variation in the temperature also we will see or not? Or
I
like only the variation on the density on.
No, I will say that it will show some changes, because this is just we are seeing at a particular altitude. I mean, just when we are looking like this, it is showing at a particular 300 kilometer, but these structures, they are kind of like a tube kind of thing, you know. So they're kind of like this. Okay, if you can see this. So so it corresponds to different height. So I believe that there should be a change in that, but I don't know any measurement or anything to that.
Yes. Thank you, Deepak.
And we have a question from the chat. It's Ipsita. I'm sorry. Yeah, he said he said really in a nested house statistically, you can distinguish between the CIR and CME driven storms regarding the EPB generation.
I will. I mean, I have not carried out any more statistical investigation here. These are the only two cases, one CIR and one CME, which definitely indicates that with respect to the onset of a storm and at what time the geomagnetic, the solar wind parameters are turning, the IMF is turning plus minus, that UT corresponds to at what longitude the sunset is happening. That really matters. So that correlation, we see some hint there, but we have not done any more cases needs to be checked to find out a comprehensive answer for that.
Okay, and I don't know if any other have more questions. Yeah, take the chance. I think they, if he's happy, he replied thank you. I have a question, not sorry, not that related to your this image from Go image.
Yeah.
You mentioned before the different terminology about this plasma bubble.
Right.
About the satellite, you mentioned the bite out, right? Bite out.
Yeah, bite out.
So yeah, I have a question about this bite out. How to the definition of bite out? In my understanding, the bite out, this shape, it's the variation or whether the electron density or variation or TC variation along time for one location. That's my understanding. But if you mentioned the plasma bubble, that means this shape, this variation along the along latitude, longitudes, or yeah. I don't know if there's a clear definition of bite out or with just say this shape we can call that bite out.
Okay, I mean, your understanding, I think my understanding is there. Whatever you told, I just agree with that, because the bite out, when they are showing the temporal evolution and for the bite out, they said that there is some structure. There is some structure which is basically moving, and that's why we see the sudden fluctuation in the electron density, which is terminal. Basically, what I'm saying, okay, that those are termed as the bite outs. But the thing is, that is again because of some irregularities in the electron density. So that's what I wanted to say, that the irregularities are treated as the bite out, the word bite out people use.
Okay. Yeah, wait. The Ipista has more question about whether he or she asked whether a moderate storm can trigger the EPB extension. I'm sorry.
Up to mid latitude.
Yeah, up to mid latitude, or it's only some intense storm.
I will say that look, particularly in this case, when I am saying, even though it is a G2 storm and but the timing when I was looking at the gold image, that time the storm didn't reach really the main phase. The sea image was 150, something like that, 140 or 150 during that time here. During this time, it is 150. So it is kind of like moderate at that time. It has not reached to 200. So by that time, we have seen the mid latitude plasma bubbles. So I'll say yes, it can. If it depends how we are saying, defining the moderate storm. If we'll say that 140, 150 nanotesla is moderate, yeah.
And by the way, yeah, about not this gold image data, it's open accessible or openly accessed or
yeah, it is open access. All these data are open access, and we release this data. I mean, when I'm talking now, we have released the data till November 5th. So just within a couple of weeks lag, this data are released to the public. Yeah.
Yeah, I think the finding of this EPB from gold the image data can trigger, very fruitful investigation. I believe that. Yeah. I think more people, more scientists or students could pay attention to these features to explain why this happened and pursue the theory support.
Yeah. No, that is, I mean, these data have so much potential. I am always excited to tell to people that, hey, if you have some ground-based kind of thing, you can always compare it. If you are seeing something in TC, you can compare with these things, because it is someone is sitting there taking the pictures all the time, and that location for continuously 3 hours. So you can compare and you can see the evolution of the things. So that is the very important thing, observing something from a geostationary orbit. So I really wish like if there will be more gold kind of observations from another two, so that we'll have a 360-degree longitudinal coverage, and that is really a good thing in the community.
Very good. So we are just about the time. Yeah, there is no more question.
Oh, there is a question, Deepak. This is fascinating. Thank you. I'm interested. How did you begin to get interested in this subject? I mean, the subject means ionospheric, thermospheric, or the plasma bubble. I don't know, but if you are asking, I did my PhD in the ionospheric thermospheric investigations that time. It is kind of like you are sitting in a table in a room. So you are doing a small thing, but you know what is happening around in the room. So in the ionospheric thermospheric system, I knew what is happening in the daytime, nighttime, the processes. This is a coupled system. So if you understand what is happening in daytime and you have some understanding in the nighttime, so you can really switch things because you want to understand everything. And particularly after joining the gold mission, I was assigned with the nighttime investigations, and that is how I landed doing the EIA EPB investigations. I hope I answered that question. That is a nice question.
Yeah, I think we can stop here.
Yeah.
Look forward more collaboration with Deepak. If any of you are very interested in the topic, I think you can contact Deepak. Yeah,
I'll be happy to share like how I will be help. I'll help, definitely help how to investigate the data, how to use the data, and what kind of things you are looking for, and can gold help in that way. So I am open for that kind of collaboration and opportunities all the time.
Okay.
Thank you.
So thank you so much. Yeah, I think we can stop here and say goodbye.
Okay, thank you very much. Yeah.
Thanks. Thank all the participants. Yeah, and look forward to see you online next time. So yeah, we close this talk today. Mm.
It was wonderful for sure.
Mm-hmm. Okay.
Okay, bye.
Thank you so much again. Yeah.
Thanks.
Thank
Thank
you.
you.
Thank you. Bye-bye.
Bye.